Okay, we're all set.
Fantastic. Hi, my name is Rob Woolley. I'm a principal technologist in the technology office at Wind River. My area of expertise is on operating systems and platforms, which includes not only Zephyr, but Linux, VxWorks, FreeBSD, and even Windows. And today I'm excited to share with you my talk on taking Zephyr RTOS to the virtual edge. Before I begin, I'd like to take a moment to acknowledge the work of my student intern, Braden Moore. Braden recently completed his co-op term with me where he focused exclusively on Zephyr, and he did an outstanding job and deserves full credit for the work done to make this possible. He has returned to study second-year software engineering at the University of Waterloo. I can't endorse him enough and highly recommend that any companies doing embedded work hire him for future co-op terms. I'm really excited to be involved with the Zephyr community. I've been working at Wind River for 15 years, and it's been a tremendous time to see how embedded has changed. The rise of Linux and open source, combined with hardware-based virtualization and compute at the edge. The emergence of edge computing is really boosting embedded even more as the number of devices is expected to flourish, as well as the compute power, capabilities, and resources at the edge. As an engineer, dealing with the various constraints is more exciting than having plentiful abundance, especially trying to balance memory footprint, security concerns, compute performance, and real-time determinism. It really forces you to think deeply about how to make use of what space you have. When Zephyr first started, we were at an impasse where 8-bit and 16-bit microcontrollers were being rendered obsolete by the upcoming 32-bit devices. There was a conscious decision not to support the smaller devices and instead set the minimum capabilities that would be required for the Internet of Things. 6 years later, I think we're starting to see the emergence of the 64-bit devices as the new de facto standard for edge computing. I think 32-bit devices will continue for some time, but for the reasons I'll state in this presentation, we'll see a shift to 64-bit devices capable of virtualization. This is an agenda for what I'm going to go over in the talk, a little bit of a background explaining why I think things are happening, what I think will happen and be implemented as a result, as well as some practical steps that we've already taken and potential future work for taking this one step further. So to start off with, why edge virtualization? We're starting to see 64-bit boards appearing in the supported boards list. The Intel 64 and ARM v8 architectures not only provide 64-bit, but they also are ushering in a lot of other modern capabilities like the cryptographic extensions and hardware virtualization, which tend to be correlated with these newer architectures. Some of the benefits of using edge virtualization include things like enabling software and hardware decoupling, which allows you to have a more modular system to allow you to integrate these pieces together in a mix and match Lego block type of way. It also increases the testability and maintainability of these devices because you can test these functional components and then not repeat the unit testing and just focus on system and integration testing afterwards because you know those blocks are guaranteed to work. Moreover, this helps improve the lifecycle management of all these devices, both the device itself and the software, leading to reduced total cost of ownership. And the extra compute power helps enable extra software-based security features, thinking of things like firewalls or integrity measurement, etc., to really beef up the security available on these edge devices. And it also allows for partition systems where you can create real-time security and safety islands to really sort of extend the architecture and the design of your edge device in new ways. Not only that, but also supporting these heterogeneous systems that we're seeing with multiple chips of different sizes, like big little type architectures, and support asymmetric multiprocessing on those types of devices. So why now? Well, with the Raspberry Pi 4 giving everybody an ARM 64-bit device in their home, and with the emerging Apple M1 laptop based on ARM, it's really pushing 64-bit ARM into the mainstream, and with that comes this blossoming software ecosystem. There's also existing pressure to shift away from some of the legacy chips and move to commercial off-the-shelf chips. And we've seen this across industries already over the past decade or more, starting with networking, then avionics, now automotive. And talking with the AGL folks last year at CES, they were already trying to popularize the trend by having standard reference hardware that people could compile their AGL for. And the ongoing automotive chip shortage that we're seeing this year due to COVID is likely only going to accelerate this trend as the chip manufacturers, the automotive car manufacturers are having trouble sourcing the legacy chips that they need. Now, I sympathize with the skeptics that might denounce the Internet of Things as being nothing new. And there is a risk of overhyping edge computing, but I think it's undeniable that consumer electronic devices are increasingly becoming present in our daily lives, be it smart doorbells, fire alarms, fitness bands, etc. And as businesses roll out their edge devices en masse, the cost of deploying these devices will be significant. Many of these devices will be expected to be maintained for a decade or more as the replacement costs are prohibitive. But this will likely compel two trends. First off, over provisioning to provide future capacity, but also tools and techniques to manage the complexity of the heterogeneous edge. And these permanent fixtures that are deeply embedded in not only our personal lives as well as inside our businesses will require continuous updates. In addition, they will also require extra measures to compensate for being remote, physically accessible, or on public networks. And I think another thing that causes this to be really urgent right now is initiatives like ARM System Ready through its IoT Ready, Embedded Server, and Server Ready classes really provide the potential for universal ARM images that boot on compliant hardware. And just like the desktop or the PCs that and servers that we're familiar with do. And this will really make the modular system integration that I mentioned before more feasible and popular, and allow us to reuse many of the software components more broadly across our devices. So what does this look like? This is a slide presented by Martin Koenig, Wind River Fellow at Embedded World 2021, and it really shows sort of the Wind River perspective on how you would leverage this technique in order to address systems that have real-time or safety-critical constraints. So in this picture, we're seeing a multi-core device, and you might have a requirement for both safety-critical and non-safety-critical guests on that device. And you can allow that mixed criticality system to exist and guarantee no interference between these nodes by dedicating them to a core and locking down sources of interference that could occur across those cores. So you can see in this example, you could have an ASIL-D certified RTOS running on core 1, and you could have Linux or Android running on some of the other cores. And because of the way the system's being partitioned, this really enables these new use cases where you have like a safety island or a real-time island, like I was alluding to before. Now, you don't have to take my word for it. Here's some examples of other projects where they're trying to pursue something similar. So the Zen community has RunX, where they're talking about using Kubernetes to actually orchestrate RTOSes using the Kubernetes infrastructure and actually launch that RTOS in a separate virtual machine and still allow it to exhibit real-time deterministic properties. There's the Edge Virtualization engine being developed through the Linux Foundation as part of LF Edge. And then we also have Acorn, which our friends at Intel presented yesterday, where you can have Zephyr and other service OSs like Linux running side by side in this sort of mixed virtual environment. Now, that one of my gripes with architectural block diagrams is there's a tendency to overemphasize the blocks and de-emphasize the glue keeping it all together. And I think an important element here to mention is that these are still embedded devices. So unlike in the cloud where the hardware is abstracted out, the applications running in the system still really care about communicating with the devices underneath. And for that communication, there's a number of different options. So you can either have direct assignment to those devices where you pass it through to the guest, and you would potentially use native drivers, but you may require some sort of para-virtualization in the native driver to make sure it doesn't cause an exception in the virtual machine. The second option are the emulated devices, drivers, and devices that you might be familiar with in QEMU. Like the venerable E1000 network adapter or the Cirrus Logic VGA card that allows you to use existing drivers with this emulated device by pretending to be the real hardware. And then lastly, you have the virtual devices, which have a performance gain because they don't attempt to be the real hardware. And so instead of having to communicate with them through individual registers like you would with normal hardware, you can instead share entire buffers and you get the performance increase. And moreover, these virtual devices can be generic in nature. So it really means that once you have those virtual drivers present in your guest, you can then take your guest and put it on any hypervisor that supports a virtual device to back them and have it just work. And this means that the virtualization can take Zephyr in new places and run on new boards without actually requiring a board support package. So then what are these use cases that this would sort of enable? Well, the ones that are near and dear to our heart are the real-time safety and security island use cases. But there are other use cases that you may be interested in as well. Continuous testing is a really important one. I've already heard this particular use case mentioned a couple times during the summit. And this allows one to take CI/CD pipelines and actually deploy the Zephyr image to some virtual cloud or virtualization engine to do hardware in the loop simulation. So you can have that faster development time by quickly iterating over different attempts and doing your regression testing. Moreover, it also supports a digital twin use case, where instead of just having metadata that describes the device, you might actually have an instance of Zephyr running somewhere in a virtual machine and actually running the same finite state machines that it would be running on the real device. Then there's also the mixed criticality use case that I mentioned before, as well as the heterogeneous computing use case, where you might have a Xilinx Zinc MP board with a R series core and a class core, and they might have an instance of Zephyr running on the R class talking to Linux running on the A class. So the backend that makes this all possible is Virtio. And this is likely a specification you may have already heard of and be familiar with. But for anyone that is not familiar with Virtio, this is essentially what it looks like. So if you have a system with a type 2 hypervisor, or even a type 1 hypervisor like Zen or Acorn, you can have a Virtio backend driver present within that, and it actually sort of presents that virtual device to the guest. And then present within the guest, you'd have a front-end driver that's able to communicate with the back end so that it knows what type of device it is and also is able to coordinate data exchange between those. Now, the interesting thing is most people are familiar with that functionality being inside of Linux in a type 2 KVM type environment, but it's not limited to that. Another possible version of this diagram would be to have the Linux on the right as a service OS, and it could also be providing the Virtio backend. And this is where it gets really interesting, especially in the types of architectures that we play with, where you may want to keep that hypervisor, that type 1 hypervisor, as slim as possible, but still have that Virtio functionality served up by Linux. Now, underneath the hood, all of this is made possible through these Virt queues, and these are virtual rings that have references to areas of memory where data can be stored, and these descriptors get passed back and forth between the back end and the front end. So in one example that I'm showing here, it's a split vert queue. So then your guest would only be able to read from one and write from the other. And there's a control mechanism in the back end to notify the guest when something's available to it. And when something is available, it would read it, it would say that it had been read, and it would put it back on the used vRing so that it could return it back to the Virtio backend driver. And this can be particularly useful in cases where you don't want to allow interference between between the back end and the front end. Now, all of this enables many different types of devices. This includes network devices, block devices, console, entropy devices, balloon devices, SCSI, GPU, you name it. And some of the transports that this can use are things like PCI bus, MMIO, or channel IO. Now, the number of vert queues you would use depends on the device type. So if you have a random number generator, then you might just use a single vert queue to pump the random numbers up into the guest. But if you have a network device, you'll actually find it uses 2n plus 1 vert queues, where there are 2n pairs of receive and transmit vert queues, and then 1 control queue. Now, this is great, but is this really feasible? So here's some proof points to show why this would be very useful within Zephyr. So we've been using Virtio within VxWorks and WinRiver Hypervisor since 2013, and that's really enabled us to support our guests with a lot of these virtual drivers to leverage the virtual devices underneath. And most recently, we've been experimenting with using Virtio with CPU shielding, and that's been particularly beneficial for hard real-time islands on Intel 64 and ARM 64 architectures, where we want to make sure that 100% of the instructions running on a core are coming from that guest, and there's no source of outside interference. Other proof points include like the Geneva Automotive Hypervisor project, where they really want to use Virtio as the standard for implementing guests on top of an automotive device. And moreover, the OpenAMP project is very interested in sort of taking Virtio one step further. There's 2 interesting talks you might want to check out. First is the system device tree talk, where they're talking about taking device trees to actually describe the guests in order to make it easier to integrate a system with multiple guests and declare it. And then there's also a talk by one of my colleagues, Dan Milla, about hypervisor-less Virtio, in which you actually do what I described before, where you have the Linux as the backend providing the service. And all of this is possible because of the fantastic work by the folks in FreeBSD that provide a Virtio implementation under a permissive license. So in terms of progress, this is where I've gotten to date with implementing Virtio on top of Zephyr RTOS. Again, full credit goes to Braden for his fantastic work. He managed to get vert queues working in Zephyr. He extended MSI support for the 32-bit x86 architecture so that we could not only get the sample app running in QEMU 32-bit, but also 64-bit using the PCI bus transport. And he implemented a virtual driver for the random number generator, and it was able to read off the vert queue and retrieve random numbers from the QEMU RNG backend. And as you can see here, it was able to retrieve those numbers, and we've already shared that on GitHub with the link at the end of the slides. And it's a fantastic starting point that Braden's provided in order to take it even further. And what are those future steps? Well, what we'd like to do next is make it possible to adapt the FreeBSD NuBus device model to the Zephyr device model. The NuBus device model is sort of an object-oriented way of hooking the driver APIs into a generic infrastructure. It makes perfect sense for FreeBSD, but it's a little bit more complicated than we have in Zephyr. And being able to provide a shim layer between those two would let us stay up to date with the latest fixes and updates and enhancements in FreeBSD without a lot of maintenance work. And then once we have that shim layer, we can actually just start pulling in the native FreeBSD drivers. And the one to start with would be the Virtio console device type. And once we've got that up, I'd also like to sort of pivot to ARM64 support by integrating the MMIO transport as well and powering that with device tree by specifying where these shared memory regions are. And then we could try looking into adding networking support, either at the lower levels with Virtio Net by making a virtual network device, or going straight to layer 4 with VSOC and allowing Zephyr to communicate with the other operating systems on the chip without needing those bottom 3 layers. And then lastly, naturally, of course, performance benchmarking, looking for throughput, latency, and determinism to try to refine everything and really go for that real-time use case. So my main interest in giving the talk at the summit this week was really to get other people involved. This is my call to action. If you're a developer and you're interested in contributing code, if this sounds exciting, I'd love to get your help. And if you're a user and you've got an interesting use case that I may not have considered, I'd love to hear your critical feedback on what you'd like to see. And lastly, if you're just interested in finding out more about this, I've provided a number of links for things that you can go and check out, projects that I think are particularly interesting and are related to this. And all of these hyperlinks will be available in the PDF that I've shared. And here's the GitHub branch if you want to try some code and check it out yourself. And that's the end of my talk. I'd be eager to hear any questions you might have. Can everyone hear me?
Yes, I can hear you, Rob.
Oh, fantastic.
Yeah, thanks a lot, Rob. It was a good presentation. It's outside of my domain, so I don't have any good questions for you.
That's totally fair. And if there are any questions that people have later, please don't hesitate to email me at rob.woolley@windriver.com.
Right, I'm going to go ahead and stop the recording. We can end just a few minutes early, Rob.
Sounds good.
Thanks again.